Hello, everyone. Today we're going to be doing some R code that relates to statistical methods for rates and proportions, Chapter 2, Section 2.2. So we're going to continue along with our example of a binomial distribution where we have a total of 25 trials and the fixed probability of success is 0.75. Probability of failure in that case would be 0.25. We're going to think about observing in our sample 23 successes. Now, in this section, we learned about the exact binomial test, and there's a function in R that will do this for you. So even though the formulas look complicated, it's pretty simple and straightforward to do this with the computer programming that we have available to us. So we're going to do an upper confidence interval for this observation. And the way we're going to do this is by setting our values of n, x, p, and q, and then telling the computer to calculate a binomial test where we observe x successes, in our case 23, out of 25 trials. We're going to do a one-sided confidence interval where we're calculating the lower bound all the way up, and then our confidence level we're setting to be 0.95. So by running all of this, we'll get our interval that should match the textbook. So our lower bound for our estimate of the true probability of success is 0.7690. And our observed probability of success with 23 successes was 92%. So one thing that's really nice about R is that anytime I create a new object, there might be things that I could pull off. So even though it gave me all of this nice output, I might be able to pull off different pieces if I know what to call it. So I can type in names of CI_upper, and that will tell me what's available to pick off using the dollar signs. So if I look at this, I could choose the statistic, the parameter, the p-value, confidence interval, estimate, null value, alternative, method, and data.name. So just by typing a few of these in, we can see what was the hypothesized null value. And since I didn't define this, it just defaulted to 50%. What's the alternative? It was a greater than test, so it was a one-sided test in this case. I can pick off the p-value, which is very, very small. And if I wanted to, I could round that to 4 decimals, so it looked a little prettier. And I could also pull off the confidence interval. So it tells me the confidence intervals and also the attributes about the confidence level, which was a 95% confidence interval. All right, so I might want to do a two-sided test as explained in the book as well. And the only thing I have to change here is the alternative statement to be two-dot-sided, and that will calculate it, the two-sided confidence interval. So when I look at this, some of the numbers have changed, right? The confidence interval is now a two-sided confidence interval rather than just getting a lower bound. But our estimate of success is the same because we still have 23 out of 25 successes, right? Our p-value is also slightly different because now we're doing a two-sided test instead of a one-sided test. And our alternative hypothesis, once again, we didn't specify. So this is assuming that the true probability of success is not equal to 0.5 for our alternative. All right, well, what if we wanted to do a more specific hypothesis test? Suppose we want to test that our true proportion is equal to 0.75 versus the true proportion is greater than 0.75. Well, we can use this binomial test, right? And we can then just add in one more piece to our function, which says that the hypothesized proportion is 0.75. Okay, So here we have that we can run almost the same code, but we just added in one additional piece, right? And now it says the alternative hypothesis that we're testing, right? We're testing, is it equal to 0.75 or actually is it greater than 0.75? So the p-value has changed as well because, as you know, the p-value is assuming the null hypothesis is true. So before, our null hypothesis was that it's equal to 0.5, whereas now our null hypothesis that it's equal to 0.75. And if we had set our predetermined alpha level to 0.05, then our p-value is smaller than our alpha level. But even better is to look at the confidence interval, right? And when we look at this one-sided confidence interval, we can look and see, is the hypothesized proportion in this confidence interval? And we see that the hypothesized proportion is actually outside of the confidence interval. So remember that our confidence intervals can match up with our hypothesis test, but the confidence interval gives you more information than just did you reject, did you not reject, right? The confidence interval gives us the interval of likely values given the sample we saw. So here, no matter if you use the confidence interval or if you use the p-value and compare it to the alpha level of 0.05, we're going to make the same decision, and we're going to conclude on the side that the alternative hypothesis is true. And we're going to state that we believe that the hypothesized proportion is actually greater than 0.75, given what we saw in our sample. All right, if you have more interest in what the binomial test function does, since this is a built-in function in R, if you just type in the function without the parentheses, this will actually give you the full R code, or at least the majority of the R code, right? And you can look through this to see the depth to which the coding took and what the codes are actually doing. This can be really helpful to make sure that you understand what things are, but it can also help you get better at coding, right? So even if you don't understand every piece of this, it can be nice to go down and say like, okay, how are things being calculated? What is this binom.test actually doing? You can come in and you can look at all these pieces. So that's something that I'm going to leave up to you guys. But I hope that you learned a lot about how to use R in this section and that you have a great day.